You should use a separate white neutral for each hot conductor in the conduit. According to the National Electrical Code, each circuit must have its own neutral conductor. Using a separate neutral for each hot conductor helps to reduce voltage drop. When current flows through a conductor, it encounters resistance, which causes a voltage drop. By having a separate neutral for each hot conductor, you are reducing the overall current flow through each neutral wire, which minimizes voltage drop. Using separate neutrals for each hot conductor ensures that the circuit is balanced. This means that the current flowing through each hot conductor is equal, which helps to prevent overloading and ensures that the voltage drop is evenly distributed. Having a separate neutral for each hot conductor provides an additional level of safety. If one of the hot conductors becomes disconnected from its neutral, the other neutral will still be able to carry the current, preventing a short circuit and potential electrical hazard. Considering National Electrical Code requirements, voltage drop mitigation, balanced circuit considerations, and safety factors, it is recommended to use a separate white neutral for each hot conductor in the conduit. When dealing with electrical circuits, it's crucial to understand the principles that govern the operation and the codes that ensure safety and efficiency. In this scenario, we have 5 single conductor number 10 American wire gauge THWN wires running through a conduit over a distance of 650 feet, supplying 120 volts to 2 security lights, each drawing 3 amps. The calculated voltage drop is 4.7 volts, or 3.9%. The question arises whether to use one white wire as a shared neutral for both hot conductors or to dedicate a separate white neutral for each. The recommendation is to use a separate neutral for each hot conductor, and here's why. Firstly, the National Electrical Code, the standard for safe electrical installations, dictates that each circuit must have its own neutral conductor. This requirement is not arbitrary, it's based on sound engineering principles and safety considerations. Secondly, voltage drop mitigation is a crucial aspect of electrical design, especially over long distances. When current flows through a conductor, it encounters resistance. This resistance causes a voltage drop, which can affect the performance of the connected loads, in this case, the security lights. By using a separate neutral for each hot conductor, you effectively reduce the current flowing through each neutral wire. This reduction in current minimizes the voltage drop because voltage drop is directly proportional to the current and the resistance of the conductor. Thirdly, a balanced circuit is essential for efficient and safe operation. A balanced circuit means that the current flowing through each hot conductor is equal and the return current flows through the neutral conductor. When you use a shared neutral for multiple hot conductors, it can lead to an imbalance in the circuit, especially if the loads on each hot conductor are not identical. This imbalance can cause the neutral conductor to carry more current than it is rated for, leading to overheating and potentially a fire hazard. Using separate neutrals ensures that each circuit is balanced, preventing overloading and ensuring even voltage distribution. Fourthly, safety is paramount in electrical systems. Having a separate neutral for each hot conductor provides an additional layer of protection. If one of the hot conductors becomes disconnected from its neutral, the other circuit will still have a complete path for the current to flow, preventing a potential short circuit and electrical hazard. This redundancy can be crucial in preventing accidents and ensuring the safety of personnel and equipment. In summary, the recommendation to use a separate neutral for each hot conductor is based on several key factors, including compliance with the National Electrical Code, mitigation of voltage drop, ensuring a balanced circuit, and enhancing safety. Adhering to these principles ensures a safe, efficient, and reliable electrical system for the security lights. Let's delve deeper into the specifics of why using separate neutrals is superior in this scenario, elaborating on the code requirements, voltage drop calculations, circuit balance, and safety implications. Considering the National Electrical Code, it's important to understand its underlying philosophy, which is to safeguard persons and property from hazards arising from the use of electricity. The code achieves this through a comprehensive set of rules and guidelines that cover all aspects of electrical installations, from wiring methods to equipment selection and protection. The requirement for each circuit to have its own neutral conductor is rooted in the need to prevent dangerous conditions such as neutral overload and circulating currents. When multiple circuits share a common neutral, the neutral conductor can become overloaded if the loads on the different circuits are not balanced. This overload can cause the neutral conductor to overheat, potentially leading to insulation damage and a fire. Moreover, sharing a neutral can create circulating currents, which are unwanted currents that flow through the grounding system. These circulating currents can interfere with the operation of sensitive electronic equipment and can also create a shock hazard. By requiring each circuit to have its own neutral, the National Electrical Code minimizes the risk of these dangerous conditions. Now let's examine the voltage drop calculations in more detail. The voltage drop in a conductor is determined by the formula voltage drop equals current times resistance. The resistance of a conductor depends on its material, length, and cross-sectional area. In this case, the conductors are number 10 American wire gauge THWN, which have a specific resistance per unit length. The total voltage drop is the sum of the voltage drops in the hot conductor and the neutral conductor. By using a separate neutral for each hot conductor, you reduce the current flow through each neutral conductor, which in turn reduces the voltage drop in the neutral conductor. This reduction in voltage drop is particularly important over long distances, such as the 650-foot run in this scenario. Excessive voltage drop can cause the security lights to dim or flicker, reducing their effectiveness and potentially shortening their lifespan. Maintaining a balanced circuit is critical for optimal performance and safety. A balanced circuit is one in which the current flowing through each hot conductor is equal, and the return current flows through the neutral conductor. In a perfectly balanced circuit, the neutral conductor carries no current. However, in reality, it is difficult to achieve perfect balance because the loads on the different hot conductors are rarely identical. When a shared neutral is used for multiple circuits, any imbalance in the loads will cause current to flow through the neutral conductor. This current can cause the neutral conductor to overheat and can also create voltage imbalances on the different circuits. By using separate neutrals, you ensure that each circuit is balanced, minimizing the current flowing through the neutral conductor and preventing voltage imbalances. Finally, let's consider the safety implications of using separate neutrals. As mentioned earlier, having a separate neutral for each hot conductor provides an additional layer of protection. If one of the hot conductors becomes disconnected from its neutral, the other circuit will still have a complete path for the current to flow. This prevents a potential short circuit and electrical hazard. In addition, separate neutrals can help to reduce the risk of electric shock. If a person comes into contact with a hot conductor, the current will flow through their body and back to the source through the neutral conductor. By using separate neutrals, you limit the amount of current that can flow through the person's body, reducing the severity of the electric shock. In conclusion, using separate neutrals for each hot conductor is the recommended approach in this scenario. This approach ensures compliance with the National Electrical Code, mitigates voltage drop, maintains a balanced circuit, and enhances safety. By following these guidelines, you can create a safe, efficient, and reliable electrical system for the security lights. Furthermore, to provide a more comprehensive understanding, let's discuss the practical implications of implementing separate neutrals versus a shared neutral, the potential challenges, and best practices for ensuring a robust and safe installation. Implementing separate neutrals means running a dedicated neutral conductor alongside each hot conductor for each security light. This does increase the amount of wiring required, but the benefits outweigh the additional material cost and labor. One potential challenge is ensuring proper identification of each neutral conductor. It is critical to clearly mark each neutral to correspond with its respective hot conductor. This can be achieved using colored electrical tape or wire markers. Proper identification prevents accidental misconnections, which could lead to circuit malfunctions or safety hazards. Another practical consideration is the sizing of the conduit. With more conductors, a larger conduit size may be necessary to comply with the National Electrical Code fill requirements. The National Electrical Code specifies the maximum percentage of the conduit's cross-sectional area that can be occupied by conductors. Overfilling a conduit can make it difficult to pull wires, damage the conductor insulation and reduce the conduit's ability to dissipate heat. Consulting the relevant National Electrical Code tables and performing calculations to determine the appropriate conduit size is important. When terminating the neutral conductors at the electrical panel, each neutral must be connected to a separate terminal or a listed neutral bar that is designed for multiple conductors. Avoid stacking multiple conductors under a single terminal screw unless the terminal is specifically designed and listed for that purpose. Improper termination can result in loose connections, which can cause overheating and arcing. Best practices for a robust and safe installation include using high-quality conductors and connectors that are rated for the intended application. Ensure that all connections are tight and secure, and that the insulation on the conductors is not damaged. Perform a thorough inspection of the completed installation to verify that all connections are correct and that the system is functioning properly. Consider using a megometer to test the insulation resistance of the conductors. A megometer applies a high-voltage DC current to the conductors and measures the resistance of the insulation. This test can detect any weaknesses or defects in the insulation that could lead to future problems. Regular maintenance and inspection of the electrical system is also important. Check for any signs of wear or damage to the conductors, connectors, and equipment. Retighten any loose connections and replace any damaged components. By following these best practices, you can ensure a robust, safe, and reliable electrical system for the security lights. Now, let's compare the separate neutral configuration with the alternative, which is using a single shared neutral for both security lights. While using a shared neutral might seem like a cost-saving measure, it introduces several risks and drawbacks. Firstly, as previously mentioned, it violates the National Electrical Code requirement for each circuit to have its own neutral conductor. This is a code violation that could result in fines or rejection of the installation. Secondly, a shared neutral can become overloaded, especially if the loads on the two security lights are not perfectly balanced. If one light draws more current than the other, the neutral conductor will carry the difference in current. This can cause the neutral conductor to overheat and potentially fail. Thirdly, a shared neutral can create voltage imbalances on the two circuits. If the neutral conductor has significant impedance, the voltage drop on one circuit can affect the voltage on the other circuit. This can cause one light to be dimmer than the other, or it can interfere with the operation of other equipment connected to the same circuits. Fourthly, a shared neutral can increase the risk of electric shock. If a fault occurs on one circuit, the fault current can flow through the shared neutral and potentially energize other equipment connected to the same neutral. This can create a shock hazard for anyone who comes into contact with the energized equipment. For these reasons, using a shared neutral is generally not recommended, especially for long runs or for circuits that supply critical loads. The small savings in material costs is not worth the increased risk of code violations, overloads, voltage imbalances, and electric shock. In summary, the benefits of using separate neutrals far outweigh the drawbacks. Separate neutrals ensure compliance with the National Electrical Code, mitigate voltage drop, maintain a balanced circuit, enhance safety, and provide a more robust and reliable electrical system. When designing and installing electrical systems, it is always best to err on the side of safety and to follow the recommendations of the National Electrical Code and other applicable standards. It is always recommended to consult with a qualified electrician or electrical engineer to ensure that the electrical system is designed and installed in accordance with all applicable codes and standards. They can also provide guidance on selecting the appropriate materials and equipment for the specific application. Moreover, to further clarify the voltage drop considerations, let's explore the calculations involved and the impact of conductor size on voltage drop. The voltage drop calculation formula is voltage drop equals current times resistance, as mentioned before. However, the resistance of the conductor is dependent on several factors including the conductor material, length, temperature, and cross-sectional area. The resistance of copper conductors increases with temperature. The National Electrical Code provides tables that list the resistance of different sizes of copper conductors at various temperatures. When calculating voltage drop, it is important to use the appropriate resistance value for the expected operating temperature of the conductors. The cross-sectional area of the conductor is inversely proportional to its resistance. This means that larger conductors have lower resistance and therefore lower voltage drop. For example, a number 8 American wire gauge conductor has a lower resistance than a number 10 American wire gauge conductor. When dealing with long runs, such as the 650-foot run in this scenario, the voltage drop can be significant, even with relatively large conductors. In such cases, it may be necessary to use even larger conductors to keep the voltage drop within acceptable limits. A national electrical code recommends that the voltage drop on branch circuits should not exceed 3%, and the voltage drop on feeders should not exceed 5%. These limits are intended to ensure that the connected loads receive adequate voltage and operate properly. To reduce voltage drop, it may also be possible to use a higher voltage power supply. For example, instead of using a 120 volts power supply, you could use a 240 volts power supply. Using a higher voltage power supply reduces the current flowing through the conductors, which in turn reduces the voltage drop. However, using a higher voltage power supply may require different equipment and wiring methods. It is important to carefully consider all of the factors involved before making a decision to use a higher voltage power supply. In the specific scenario of the two security lights, each drawing 3 amps, the total current is 6 amps. With a 120 volts power supply and a 650-foot run of number 10 American wire gauge conductors, the voltage drop is calculated to be 4.7 volts, or 3.9%. This is slightly above the National Electrical Code recommended limit of 3% for branch circuits. To reduce the voltage drop, you could either use larger conductors or use a higher voltage power supply. Using number 8 American wire gauge conductors would reduce the voltage drop to approximately 3.0 volts, or 2.5%, which is within the National Electrical Code limit. Alternatively, using a 240 volts power supply would reduce the current to 3 amps, which would reduce the voltage drop to approximately 2.35 volts, or 2.0%. In summary, voltage drop is an important consideration in electrical design, especially for long runs. To minimize voltage drop, it is important to use the appropriate conductor size, consider using a higher voltage power supply, and follow the recommendations of the National Electrical Code. And to expand on the safety aspects, let's discuss grounding and bonding, which are essential for protecting people and equipment from electrical shock and fire hazards. Grounding is the process of connecting the electrical system to the earth. This provides a low impedance path for fault currents to flow back to the source, which causes the overcurrent protective devices, such as circuit breakers or fuses, to trip and energize the circuit. Bonding is the process of connecting all of the metal parts of the electrical system together. This includes the metal conduit, metal enclosures, and metal equipment. Bonding ensures that all of the metal parts are at the same electrical potential, which reduces the risk of electric shock. The National Electrical Code requires that all electrical systems be properly grounded and bonded. The grounding system must be connected to a grounding electrode, such as a ground rod or a metal water pipe. The bonding system must be connected to the grounding electrode conductor. In the specific scenario of the two security lights, it is important to ensure that the metal enclosures of the lights are properly grounded and bonded. This can be achieved by connecting a grounding conductor from the metal enclosure to the grounding electrode conductor. The grounding conductor must be sized in accordance with the National Electrical Code. It is also important to ensure that the metal conduit is properly bonded to the metal enclosures. This can be achieved by using bonding bushings or bonding lock nuts. In addition to grounding and bonding, it is also important to use ground fault circuit interrupters in circuits that supply receptacles in wet or damp locations. Ground fault circuit interrupters are devices that detect small imbalances in the current flowing through the hot and neutral conductors. If an imbalance is detected, the ground fault circuit interrupter will trip and energize the circuit. Ground fault circuit interrupters are very effective at preventing electric shock. In summary, Grounding and bonding are essential for protecting people and equipment from electrical shock and fire hazards. The National Electrical Code requires that all electrical systems be properly grounded and bonded. It is also important to use ground fault circuit interrupters and circuits that supply receptacles in wet or damp locations. Finally, after thoroughly discussing the technical aspects, safety considerations, and code requirements, it's crucial to reiterate the importance of engaging qualified professionals for any electrical work. Electrical systems can be dangerous, and improper installation or maintenance can lead to serious injury or property damage. A licensed electrician has the knowledge, skills, and experience to design, install, and maintain electrical systems safely and effectively. They are familiar with the National Electrical Code and other applicable standards, and they have the tools and equipment necessary to perform the work correctly. Attempting to perform electrical work without the proper training and qualifications is never recommended. It is always best to leave electrical work to the professionals. In addition to hiring a qualified electrician, it is also important to obtain the necessary permits before starting any electrical work. Building departments typically require permits for electrical work to ensure that it is performed in accordance with the local building codes. Obtaining a permit also allows the building department to inspect the work to ensure that it is done properly. In conclusion, when it comes to electrical work, safety should always be the top priority. Engage qualified professionals, obtain the necessary permits, and follow the recommendations of the National Electrical Code and other applicable standards. By doing so, you can ensure that your electrical system is safe, reliable, and efficient.